Newton's first law of the motion, or law of inertia. And what it says is a body in uniform motion remains in uniform motion, and body at rest remains at rest, unless acted upon by a non-zero net force. So here we have a number of new terms we have to understand. So it's a uniform motion, it remains uniform. And a body at rest, what is a body at rest? And what is net force? Well, these are new concepts we try to understand, but to make this clearer, I'm going to provide you with some example. Just try to explain what is happening in this case. Okay, so what it says is a body in uniform motion remains in uniform motion, and the body at rest remains at rest unless acted upon by a non-zero net force. So more difficult. So watch this carefully what is happening. That Malteser is resting on the dashboard. And, well, this is when the car goes to a right turn, the Malteser starts to move. So we're trying to understand how does this motion fits into the first law of the Newton. And perhaps this is one of the questions we find an answer at the end of this lecture. So we can explain why the Malteser resting at peace, what is causing for that motion to change. So this is apparently a change of motion. A particle is resting on the dashboard. Suddenly, it starts to move. So what is responsible for that move? We know that this is happening during a right turn. And the other question is, what happened to this truck? So can anyone explain what is this scenario? Okay, and then what happened? So which force? Can you explain the nature of the force? You are saying the force is responsible for that truck to be like so? Negative force applied to the rock, Okay? What triggered this motion? How this motion was triggered? Stopped. And so you're saying that a car going with a steady motion, so this is not a change in motion, that's steady, it doesn't change with time. Suddenly when it stops, that's a change in the motion, and that change in the motion creates a net force. That net force moves the rock, and then rock moves faster than the car, and this is why it is happening that. All right, good explanation. So we try to put what what he explained, we try to put this into the context of laws of the motion, right? So this is an excellent example. We have a uniform motion. A truck is moving with a uniform velocity, uniform motion, and suddenly this motion changes, and as a result of the change, a net force, a non-zero net force, is developed in the system comprising of the truck and the rock. And as a result of this force, it brings the stone forward, and that smashes the car. So using the same principle, we should be able to explain how this Malteser chocolate starts moving, starting from the rest. So why during the right turn, suddenly a change in motion occurs, and as a result of that change in motion, a force develops, and that force gets the ball rolling. And so this is the problem, and we're trying to put this into a mathematical frame to find out a quantitative explanation. Okay, so one thing we need to realize in this formulation is the inertial frame. Inertial frame is a fixed frame which is not moving, but living on Earth, we realize that Earth has a velocity, has a motion. So for Earth to be regarded as an inertial frame, we can only model the problem which have velocities small compared to the velocity of the Earth. If the velocities are much larger or comparable, if the time frames are comparable to what is needed to describe the motion of the Earth, so Earth cannot be classified as an inertial frame. Okay, so we get back to this multi-choice question. I mean, you will be answering this question, but try to, let's have a sneak preview of the question. That is, a ball is moving within a cylindrical surface, and this is just for the sake of understanding. We are looking at the top view of the motion, but that is resting on a table. This is a horizontal table, it's not moving vertically. And this cylindrical face is not perfect, it's just a portion of the cylindrical face. So when it reaches the end of this cylindrical section, the motion is going to change, right? Or remain the same motion. Whether it's going to go through a circular motion that is remaining into the same situation, or it goes straight, or that drops. So which one is the answer? That is closely linked to understanding the laws of the motion. We get back into this and try to get you to answer it. All right, so that was the first law of the motion. I repeat the phrase describing the first law of the motion, that is, if an object is through a uniform motion or is stationary, for that state of motion to change, you need a non-zero net force to change the motion. If the net force is zero, then the particle keeps moving with the same uniform velocity, or it remains stationary. That is the first law. And the second law of the Newton, this is how we define development of the net force in an inertial frame when a particle, a mass, having an accelerated motion. So how this motion can be described. All right, the first thing first, what is the net force? Anyone knows the net force? So net force is when you have a system which is acted by a number of different forces. So in this example, two people are pushing a car, and you remember from previous chapters, vectors, they follow a certain rule for summation or subtraction. And I mentioned to you that force is a good example of the vector. So if we represent the force applied by these two persons with F1, F2, in order to add these forces together, you have to add them like vectors. They are not added like numbers. And with this system, the system with two forces, the outcome of these two forces is one single force. We call this the net force, the resultant force. In other words, you are putting two forces as input, F1, F2, there are inputs, and the resultant, the output is the net force. And that net force from every system is different. That is the trick. Given a particular unique system, we should be able to identify the forces, and then when you realize the forces, we have to combine the forces together in this system to find out what is the resultant force. Because in applying the Newton's law, what does matter is not the individual forces, but that is the net force. For the whole system, you have to combine all forces together. First, you identify which forces are active. Then you combine them, and as a result, outcome is the net force. Once I know the net force, I should be able to explain how the mass of the system would accelerate as a result of that net force. All right? So how this rule, how this law is different with the first one? The first one says whenever the net forces are 0, the particle, the mass, is either going through a uniform motion or is stationary. We don't make a distinction between uniform velocity or stationary. From motion point of view, both of them, they are not changing the motion. So since they are not changing, that means the net force is 0. But when the net force becomes non-zero like this one, according to the second law of the motion, the force is going to make the mass to accelerate. And how this accelerates, that is the relation. It's known as the second law of motion, second law of Newton. All right, so here we are explaining this like a physical phenomena. That is not simply saying that force is a function of mass and acceleration. That's not a good explanation. So, in other words, if you multiply mass by acceleration, as you see here, mass multiplied by acceleration, this is not a force, right? Mass is an inherent property of the material. Acceleration is something which describes the motion. So F equal to ma, that's the second law of the Newton. What it says is when you change the motion of particle m, this can be done only if the net forces are non-zero, and that is proportional to the net force. The second example here is you have this is a jet, and this jet is the propulsion is by interaction between gravitational force and friction force, lift force. So all these forces together, they're causing a net force, and of course engine, the turbine used for this jet, they are producing an axial force forward. So how the motion of this jet can be described? Before we can answer this question, you have to combine all these forces together. So how do we combine the forces? Previous chapter. Vectors. Anyone remembers how do we add the vectors together? Adding the vectors? Yep.
The I direction together and the J direction together, they add together.
Excellent. So in a two-dimensional system, if you identify the forces, to add them together, you resolve the forces. Each individual force, we resolve them into the x and y component, and then you add all the I components together, all j components together, and that is called net forces. So you can make the resultant x forces, resultant y forces, they form a triangle. That triangle, the third side, give you the resultant force, or the net force. That net force, in the scenario that net force is non-zero, it's going to cause the mass to accelerate. If the net force is 0, what's going to happen? First law of the Newton. If the net force is 0, either the force remains stationary, or if that is moving with a constant velocity, it keeps moving with a constant velocity. So for that state of motion to change, there is a critical ingredient. And what is that critical ingredient? A non-zero net force. What is net force? Net force is, with a system, you identify all forces involved, and then you try to combine all forces together. And when you find the resultant, we call this net force. Net force dictates how the mass is accelerated. And with the non-zero net force, the law we are using is called the second law of the Newton. And that law can be represented in different ways. I mean, one way is you describe the motion by its acceleration. One way of describing the motion is if you know the acceleration, you can describe the motion. So how this acceleration is a vector. It's not a scalar. It has a magnitude and a direction. So right-hand side, you have the force, which is the vector. Mass is a scalar. It's an inherent property of the particle or the system. So what happens if you divide a vector by a number? The outcome is still a vector. Right? So both sides of this equation are vector. Acceleration is vector. Force is a vector. All right? Or what you do is, if in the system you know the motions and you don't know the forces, can you use this law in a reverse order? That is, given the acceleration, are you able to estimate the net force? How this can be done? Any suggestion? So imagine with one particular problem, instead of having the net force, you have a description of the motion. You know that this is a one-dimensional motion along a straight line. And for that, you know the constant acceleration. And also, you know the mass of the system. Are you able to estimate the net forces? Right, so what about we go from the right side of equation to the left side? So you have the mass, you have the acceleration, just the product gives you a vector, and that vector is equal to the net force, not the individual force, but the net force. Later on in the upcoming chapters, we introduce a concept of momentum. Momentum is the product of the mass by velocity. So, second law of the Newton, in the mathematical sense, can be defined as variation of the momentum in the unit time, and that is equal to the net force. So all these three different forms, they are obtained by applying the second law of the Newton. All right. So what does mass tell you? If an object is transferred, I mean, if you take a particle from here, you take it to the moon, take it to another part of the universe, is the mass going to change? Yes, no? So 1 kilogram mass here would be how much on Mars? 1 kilogram. So mass is the property of the particle. It doesn't change no matter how much gravitational force is there, right? So mass is a descriptor. Some systems are heavier than the other system. So this is the example presented here. The very same truck is driving full of loads here, and the same truck is without the load. So if in these two scenarios the driving force or the net force is equal, what conclusion can you make using the second law of the Newton? Same truck, same driving force, the masses are different. In the second case, it's full of load, is heavier. In first load, there is no load, it's much lighter. So what conclusion can you make? Which one? So the top one has a higher acceleration or lower acceleration? Higher acceleration, right? So this is a demonstration of the Newton's law. So the car has the same power, the truck has the same power, same engine. So it means for this car to accelerate, it's not just a matter of how much driving force is there. You are not changing the engine. The engine is the same. But if that's heavier, you can accelerate the car less if the car is lighter, applying the same force, you could accelerate this easier. So that is just another description of the Newton's second law. All right, so before getting into the problems, we have enough questions to start an engaging activity. So I would like you to take your Wi-Fi enabled devices, and here we try to run a test. Okay, so I'm going to have 4 teams. For each team there would be a champion, so volunteers to join the groups, and then everybody else joins their group. So you'll be competing in 4 groups with maybe 10 multi-choice questions. So your name is? Lorraine. So I give you the room number. Would you join the first group? So we identify that group under your name. All right. Group blue is Lorraine, and magenta, Adam. Where is Adam? Your second group. So people want to join Adam's group. And lime group, Alex. Alex, hello. You'll be the third group. And peach group, any volunteer for peach group? What's your name, sorry? Lily would be the peach group. Okay, now you could use the class name, go to the Socrative, www.socrative.com, and for the class name, please type my family name. I just put this here for everyone. Okay, so this is Socrative, and you have to, excuse me, you'll be joining Socrative with a student login, and when you log in as a student, it asks you for the class name. For class name, please type my family name, Kodam, K-H-O-D-D-A-M, that's the class name, and then put your student ID as the name. For your name, put your, that's a class name. Yeah, that's how you log in as a student. Now I have 16, 18, 19 students join. Okay, 44 students. We still are waiting for 24 students to join. Okay, blue and lime are neck to neck. Okay, lime is the winner, and the third one is peach, and right, very close competition. Thanks very much for all your inputs. Okay, now what we do is we're going to find explanations for the question. We go through the question one by one. All right, now you may want to log into the group again, or maybe you're already logged in. So first question, if a ball is released, then it rises above the dotted horizontal line. Put your answers. We have 37 students logged in, so only 31 participated, if anyone hasn't joined yet. So we would like to have as many answers as we could. 27 out of 33. 4 more should participate, 36. 3 more students. Okay, so let's have a look at the answer. Okay, and the right answer is answered correctly. The correct answer is D. Why the ball reaches to the same height? The explanation, we're going to see that during the upcoming chapters. So when we deal with the energies, 2 types of energy, gravitational energy and kinetic energy, that would explain why the ball reaches to the same level. But for now, 82% of a student answered to this question correctly. Next question. Okay, 38 is good. When 38 answers, we look at the right answer. 2 more. 2 more answers, please. Okay, and the right answer is C. Okay, so that's an ideal situation, but in the absence of friction, when the ball is released, because it cannot reach the same height, it would roll forever. That's an ideal situation. So non-zero net force, everyone knows what the net force is. If the net force is non-zero, that is referring to the second law of the Newton. Okay, 10 more answers. Okay, 2 more answers and that's it. We look at the answer then. Okay, the only wrong answer is B. Both A and C are correct, so B is the only wrong answer. And according to the Newton's law of the motion, if the net force is non-zero, the motion is going to change. It's not remaining as it is. So the non-zero net force is responsible for change in the motion. So next question, anyone remember the right turn? Okay, so you realize here the system is not a inertial reference frame because of the acceleration. The reference frame is the car is moving, the car has an acceleration. Because of that acceleration, the law of motion doesn't apply here, right? So the right answer is F. 89% got it right. All right, so it seems the truck driver didn't know about the law of the Newton, and when they packed the rock, they didn't know what happens when they brake. And the right answer is C. 97% got it right. Great. So this is very interesting. I would like to see how you perform with this one. Okay, can I have your attention, please? This is a very important question. I want to see why the correct answer is B, 97% correct. And is this a change in the motion? First law of Newton, it says when there is a change in the state of the motion, if there is no external force, the motion remains as it is, either stationary or it doesn't change. Second law of the motion says what is responsible for change in the motion is external force. And we would like to discover, in this case, is there a change in the motion? So to answer the question, let's look carefully at this diagram. So the motion is described by the velocity. So first we have this velocity here, v1. Then we have v2, v3, v4. Just first question, how do you compare v1, v2? Are they the same? Are these two velocities the same? No. Why not? The magnitude is the same. So for a vector to be identical to another vector, two requirements. First is the magnitude. Second is direction. So in this case, which one is violated? Direction has been violated, right? So as long as the ball is resting against the cylindrical face, there is always a change of velocity, not because of the magnitude, because of the direction. So because of that change into the motion, there has to be a non-zero net force. And when the non-zero net force exists, that is the second law of Newton, right? And during that stage, there are going to be a net force applying between the ball and the surface. So for every individual instance, you have one contact force between the ball and the surface. That is when the state of motion is changing, but the minute it releases the surface, that contact force disappears. Everyone can see this? So once the ball is leaving the cylindrical face, the contact force or net force becomes zero. And when the net force is zero, what happens? Which law of the Newton? Zero net force. Which law of the Newton is that? First one, right? With the first one, it says with the zero net force, the motion remains as it is. So from that point forward, we should expect no change into the velocity. So the velocity remains as, when this one is leaving the surface, the velocity remains as v4, and it keeps moving as v4. So both the magnitude and direction of the motion becomes the same. So this example is an excellent example for the first portion, demonstrates the second law of the Newton when the net force is not zero. Due to that non-zero net force, the motion keeps changing. So there is an acceleration. That acceleration we are going to explain later. That's called centripetal acceleration. All right? But when the ball is leaving the cylindrical surface, the net force becomes zero. There is no contact force between the ball and there is no surface, right? So this is when we are eliminating the net force. So zero net force, that is the first Newton's law. With the zero net force, what we should have is the motion remain as it is, either stationary or moving with a constant velocity. And you see this is a constant velocity. V4, from that point forward, the velocity is V4. And all right, I'm sure everyone got the right answer, but perhaps not with this much explanation. All right, let's go to the next one. So is this a fake photo or what? Haven't you seen people performing that? Yeah? So I assure you C is not an option. It's a real photo. So only 3 options. Okay, and the right answer is, which one? Which one is the right answer? Let's see. 100% got it right. So let's put this into the Newton's principle concepts. So we want to explain this using the Newton's principle. So for that, I mean, here you have a particle. You take the car and the passenger as a particle, and this old man is applying a force from where? So this cable is the force which is applied to here, and that particle, whatever that is, this is moving with a velocity, right? So if this velocity is applied spontaneously, suddenly if that velocity is applied, or if the velocity is not constant, there is going to be an acceleration, a non-zero acceleration. For that non-zero acceleration, according to the second law of Newton, there's going to be a non-zero net force. And that non-zero net force is going to be huge. So when you apply the force spontaneously, the chances are you're going to lose your teeth. But when you apply this with a constant velocity very slowly, you only develop a zero net force, and that zero net force is something can be tolerated with that teeth. It doesn't harm the teeth. But if you apply this quickly, we are going to see this in upcoming lecture on the concept of momentum. But here, just to put it simple, if you change the velocity so slowly that acceleration is negligible, then the net force is going to be zero, and this is actually the case here. Next question. Okay, the same truck, same driving force. The only difference is one truck is empty, the other truck is fully loaded. So what do you reckon how the accelerations are going to be different? Okay, so the right answer is B. 63% got it right. And if you look at the pictures, I mean the picture is speaking for itself. Identical forces, the red arrows are of the same size. The black arrow acceleration, this one is larger. And why is that? Simply because of the second law of the Newton. Second law of the Newton says for a particle to accelerate, the net force should be non-zero. So for both cases, there is a non-zero equal net forces. So you have the product of mass acceleration for initial case equal to the product of mass acceleration for the second case. Since the forces are equal and the mass in the first case is smaller than the second case, therefore you will have the acceleration first case larger than second case in order to keep the balance between equation. So smaller number multiplied by larger number equal to the larger number multiplied by smaller to keep the balance between two forces, because we know both forces are equal. So in other words, if we want to solve this mathematically, so that is how this is done. So you have F for first case is equal to the F for second case. Mass for first case times A1 is equal to mass for second case multiplied by second case. And then you have first mass divided by second is equal to A2 divided by A1. So this fraction is, this is smaller than 1. Right, so this is smaller than 1. So is this one. So A2 smaller than A1. All right, let's go to the next question. Okay, there is something zero here. That zero something is called apparent weight. Sorry, yep. Yeah, so here apparent weight is 0, and like I said before, mass is a property of an object. It doesn't matter if that's Mars, anywhere in the deeper space, the mass remains the same. But something that changes is weight. Weight is the gravitational force. And this astronaut is orbiting, so the motion is a circular motion. With the circular motion, there's always a centripetal acceleration. When that centripetal acceleration neutralizes the gravitational acceleration, so that is when you have the weightless condition for an astronaut. Or sometimes this happens in an elevator when you get a balance of the elevator's acceleration and the gravitational weight. So here the apparent weight is 0. We call that the force of gravity. 71% correct. Let's go to the next question. You got it? Well, once this is an orbit, that's a circular motion. In that circular motion, even if the velocity is constant, the centripetal acceleration is proportional to the square of the velocity divided by the radius. So when that equates the gravitational force, that is when the astronaut feels weightless. All right? Okay, here is this true or false? A heavier skier beats a lighter skier. Do you agree with that? All right, since I'm going to solve a detailed analytical example on this one, please at this stage just you take my words for it. Maybe I forget to put the right answer in this test, but I'm going to give you a detailed solution for this problem. So don't worry now. What about this one? The orbiting? Yeah. Orbiting is not a motion along a straight line. Yeah, we are going to cover this under circular motion. When an object goes through a circular motion with a constant velocity, there is always a centripetal acceleration developed, and that centripetal, you remember this illustration, the magnitude of velocity is same, but the direction keeps changing. Because of that direction change, that means the acceleration is developed. And that particular acceleration, we call it centripetal. Don't worry at this stage, because this is an upcoming topic, we elaborate on that later. It's not gravity zero, it's apparent weight is zero. Apparent, yeah. That means the resultant between centripetal and gravitational acceleration. Apparent weight, yeah, apparent weight. Okay, so this question, that refers to the third law of the Newton. We haven't covered this yet, but that seems something obvious. It's called action-reaction. When objects are at contact, two forces develop, and these forces are equal in magnitude, opposite in direction. These are called action-reaction, and according to the Newton's third law, action and reaction are equal and positive, and they come as pairs. There is no such a thing as one reaction force. It's always reaction and action. So they develop due to the contact, and in this case, that is an example for the third law of the Newton. So the right answer, everyone got it right. You didn't know about the third Newton law, but somehow, yeah, you. And what about this one? The same principle, action and reaction. So this is the answer. So still the same principle, that's the third law of the Newton, action and reaction are equal, and for that reason, it's always these two forces are equal. This is a very tricky question. I'll be surprised if anyone can explain. Maybe you find the right answer one way or another, but I'll be very surprised if anyone can give me the explanation behind it. All right. Please pay attention. When she throws the object, either the wrench or the hammer, they both produce the same force. So which one is heavier, one is lighter, but both of them, they are producing the same force. So which one should she throw to go faster? The hammer. Okay, that is the right answer, but I want an explanation. All right, anyone can explain? So this is a controversial question. 46% wrong, 55% right, but even those who got it right, can you explain? Yes, force is the same. Force developed due to the hammer or due to the heavy, the force is the same. So why the hammer makes her to go quicker? Yes, so can you explain? Could you listen to your classmate, please? Could you explain it for everyone? Can you listen, please? Yes, go ahead.
When you get rid of the hammer, you're throwing away more weight, and the force is the same, so you're doing squared acceleration.
Did anyone listen what he said? So before releasing the hammer, releasing the hammer, what was the total weight? The total weight was her weight plus the hammer. But when she is releasing the lighter wrench, the total weight is less. So if they are producing the same weight, because in the second case when she is releasing the hammer, she becomes lighter. According to the second law of the Newton, if the force is equal, and in one case you're dealing with a light system, that would accelerate higher. And if that accelerates higher, that means she reaches to the International Space Station faster. Okay, well done. That was a very good question. So that means you are well aligned with the class. This is the last one. If someone can explain the answer for this question, it means you understood both first and second law of the Newton. So let's restate the question this way. That the left side guy, he only can apply 500 Newton. That's the unit for the force. That's the maximum he can apply. But the most strong person, he can apply something like 1,000 Newton. So what happens if the stronger person pulls this harder, he applies more force? What happens? Is this going to change the reading of the thing? Why? Why do you think it changes? Yep. All right, so that is the trick. I mean, this is what we mean by the net forces. We just imagine that a stronger person is applying a larger force, and then the right-hand side guy, he only applies 500 Newton, and then as a result of that force, he has to follow a motion, right? This is not a stationary system. So they walk together, but still the reading of that's a net force. This is the maximum the guy can apply. He cannot apply any. So that means if the force increases, as a result, the system starts to move, the state of the motion will change. Now, a stationary system, this is the state of the system, now it becomes an accelerated system. So it means that the second person, that the weaker person, starts moving with the system, but that doesn't mean the force would increase. So the whole system starts to accelerate, but the reading of the force, that's an internal force. The internal force can exceed from, according to the law of the motion, tension inside the cable, everywhere inside the tension, every point inside the cable, the tension remains the same. So if one person can apply 500 Newton, you can't have a scenario with 500 forces here, 1,000 force over there. It doesn't satisfy the equilibrium of the forces. Now, thanks for this participation, and now we just get back to the lecture where we left this. So, all right, now this is a problem we try to solve together. Just read the question for a few seconds, and then we see how. All right, these are the key steps to solve every problem. 4 steps are to interpret, to develop, evaluate, and assess. How individual steps apply to this problem, we will see. With the interpretation, what you need is to identify the key pieces of information. So you are given the mass for the car, and it starts from the rest. That means initially the velocity is 0. Then it reaches to 20 meters per second. So during this period, there is an acceleration involved. And then you have the duration of the time, and you know the motion is a straight line. These are very important piece of information. If that was a motion along a circular path, you had absolutely different theoretical model to solve. So this is a straight line motion. And then runs a bend radius of 85 meters. That's a different type of motion at this stage. And during that round bend, the velocity is constant. That is 20 meters per second, centripetal motion. And here we would like to find out the net force which is acting on the system. So this is the key informations are given. So for both situations, the net force is not 0, and for that reason we are using the second law of the Newton. So development typically involves a simple schematic diagram, and in that you simplify the system into particles, lumped masses, and that is very essential to solve the problem. Here the car is represented by a simple particle, a lumped mass, upon which a net force is acting. And so second law of the Newton, that is when you start the evaluation. So to evaluate, we bring the second law of the Newton, that is the magnitude for the net forces is equal to the mass multiplied by change into the velocity divided by change into the time. And all these numbers are highlighted in the statement. So you just substitute the values, and from there we'll find out the net force to be 3076 Newton, or in terms of kilonewton, that's almost 3.1 kilonewton. All right, what about the second case? Second case, the development is different. Initially, it is moving along a straight path. Second stage, it rounds a bend, and for that bend, we take this as a circular motion. So that is the development for the second stage. So path is given by the red dot line. Car is represented by the lump mass, the red lump mass. And during this stage, there is a net force developed toward the center. And for this scenario, we know the centripetal acceleration is proportional to the square root of the velocity divided by radius. That we would elaborate later in the upcoming chapter. But for now, just take this equation. And for this case, the net forces, that's the second stage when the car is driving on a circular path. So this would explain, you remember that in the commercial, when the driver went into the circular path, the particle started a motion. That motion was due to this centripetal acceleration. All right? So for every circular motion, you feel that centripetal acceleration. When was last time you had a merry-go-round? Have you done merry-go-round in the play zone? So when you are standing in a merry-go-round, you feel you are being thrown away. You have to keep hold of the handle to stay where you are. So in this case, you find out the net force to be, just substituting the values. This net force happens to be much larger than the previous case. That is 5.6 kilonewton. All right, so in terms of assessment, you have to make sure that the units are correct, and we do the assessment regarding the magnitudes, behaviors, and all that. All right, so there is a video cast, you can find it on the canvas, that is called Acceleration of an Ice Puck. So just make sure you watch that video cast. That would give you some insight for this. Okay, so second law of the Newton, what it says is a non-zero net force is proportional to the mass and is proportional to the acceleration of the system. So what is the unit for the force? We never mentioned the units. So we define 1 Newton as the product of 1 kilogram. 1 Newton is the force which a 1 kilogram mass experiences when it undergoes an acceleration of 1 meter per square second. So that is a definition. So let me repeat the definition. 1 Newton is defined as the force exerted to a 1 kilogram mass when this mass is accelerated by 1 meter per square second. So these are examples when we have two types of forces here. Contact force. Contact force is when objects are in contact together, when something is resting against the surface. Do you think there is another type of the force? Can you think anything other than the contact force? What other type of force can you name? Gravitational force. Is it a contact force? So we could classify forces as contact, non-contact when a first object is under the magnetic field. So the nature of the force is not a contact force. That's a field force. So when we are solving a problem with the laws of Newton, we have to account for both types of the forces, whether they are contact forces or they are field forces. So when a force is acting at a distance, that is, examples I gave you, these are gravitational force, electromagnetic force, and when a particle is moving around a circular path, so the force due to the centripetal acceleration, so forces are either contact or they are acting at a distance. Force of the gravity, so that question we dealt with in the engaging activity. That was similar to the case of the astronaut. Here, a person in an elevator, the elevator has its own acceleration, and this person is acted by the gravitational field. So at some certain scenario, he or she feels the weightless situation because of the net force or apparent weight becoming zero. So second law of the Newton, it's highly relying on the net forces, but an interesting question is, how do we get the net force calculated? It's not easy in a general case to find out the net force, and one technique to obtain the net forces is called drawing free body diagram. So that abbreviation, that acronym, try to remember this. From now on, most of the problem you solve, they are one way or another related to the free body diagram. What does this free body diagram mean? So you have a system. A system is composed of a number of lumped mass which are moving, and then you can isolate this lumped mass from its environment. How do you define the system? That is your option. I can isolate a complex system by drawing the borderline, and this is up to me how I want to draw this borderline. If I make the borderline larger, my system would encompass anything within the border. If anything outside this borderline becomes environment, anything inside becomes the system. So this system will tell you how to calculate the lumped masses. Let me give you an example. If there are two boxes which are connected with a cable to the wall, and then if I decide to have my system like so, so net force here is gravitational force, and that one force is going to be here. The sum of both these forces are called the net force. But if I choose my system to be a bit larger, this is my system. So anything outside this dotted line becomes environment, anything inside becomes the system. So for this new system, the net force is what? The net force is, you have two gravitational force acting here and one tension force in the cable to keep the system in equilibrium. So it's the most challenging part of the problem for this chapter and few upcoming chapters. That is, you have to choose the right system, how to isolate the particle from their environment. Depending how you isolate the system from environment, the net force is going to change. And for every system, you can write the law of the motion. You can write the law of the motion for this system, or you can write it for the second. All right? So that case, you have something hanging, and the forces acting upon are the gravity force here, and also you have a cable tension. So in this case, net forces are the sum of gravitational force and the cable force. Question: the hanging object is moving with a constant velocity. What would you expect as a net force? Do you expect a non-zero net force or the zero net force? I repeat my question. The hanging elevator, whatever, that is moving with a constant velocity, right? So do you expect a non-zero net force? Do you expect the net force to be zero or non-zero? Constant velocity. Zero. Can you tell me which law of the Newton you used for this answer? First one. First one, it says if a system is stationary or moving with a constant velocity, then the net force is zero. If I tell you for the very same system, a box attached with a string, and then if the net force is non-zero, would you expect this box to have a zero acceleration or a non-zero acceleration? Non-zero. And which law of the Newton do you use? Second one, right? Great. So for this very simple case, it seems everyone is in the same page. When we can generalize the concept to the more complex scenarios, and of course the problem you are dealing with are far more complex than this one, but the big idea is the same. The big idea is either the motion changes or the motion doesn't change. The only thing which can change the motion is force. If there is no net force, the motion remains as it is. Okay? So I make you an analogy. Someone is sleeping. All right? He or she remains sleeping forever unless you yell at them, pour water on them, right? So that's the only way you can change their state. A sleeping person become awake. How can you do it? Non-zero is here to yell at them or to wet them. The same thing in mechanics. An object is stationary, is moving with a constant velocity. That means no one has yelled at them, no one wetted them, right? Someone is waking up. That means a non-zero external force applied to change their status from sleep to awake, from stationary constant velocity to accelerating motion, right? So that is the big idea. Hope my analogy didn't make you more confused, so you find it relevant. All right, here we have to make the free body diagram, and in this free body diagram we represent the elevator with a single particle. That particle, it doesn't matter, you put it as a dot, you put it as a box, whatever. The important thing is all gravitational force is lumped. They are acting at the center of gravity for that box. And what about the direction? For gravitational force, what is the direction of the force? Toward the center of the Earth. And tension of the cable, in this case, that's a one-dimensional problem. You only need one coordinate axis. So along the gravitational force, you pick your coordinate system. For every problem to be solved, you do need to have coordinate system. Why? Because we have to deal with the vectors. Vectors have two components. So how do you know about the choice of coordinate system? Choice of coordinate system is subjective. All right? It's not a unique definition. I mean, you could have your coordinate system in either way you want, but some coordinate systems, they're going to make the solution much easier than the others. So it's always recommended you pick your coordinate system at least in accordance with the motion. So you pick your coordinate system along the motion and normal to the direction of the motion. And since we only study the one-dimensional motion, it's not difficult to choose how to locate the coordinate system. In this case, we have one axis along the gravitational force, so you isolate the system from its environment, and that is the dotted line here. And to isolate, you have to replace where you cut this isolated this from environment, you have to replace it with a tension force. So gravitational force, tension force, and the sum of these two forces, that makes the net force. And net force would tell you what type of motion you have, whether this is a stationary, constant velocity, or accelerated motion. If that's stationary, that is first law of Newton. If that's moving with the constant velocity, first law. And if that's accelerating, that's the second law. So here, an skier is going along an inclined line, and we want to isolate this from environment. Well, the skier with the ground, they have a contact force. Here we show this with letter N. Also, there is friction force between in a tangential direction. Gravitational force always is vertical. And then to solve this problem, this is a vector. The vectors are two-dimensional. You need two coordinate system. And interestingly, in the very same problem, both laws of the Newton apply. Normal to the inclined surface, the skier does not move. So if you just look at the normal direction to the path, this is the first law of the Newton. Because the net forces, there is no acceleration associated normal to the face. So two consecutive scenarios, the particle is not getting farther from the incline or not getting closer to the incline. So normal to that surface, there is no acceleration. And because there is no acceleration, the net forces should be zero along that axis. But what about parallel to the inclined surface? Parallel to the inclined surface, the net force is not zero, and that net force is proportional to the mass, is proportional to the acceleration. So very same problem, you resolve that into two net forces, along and normal to the path. Normal to the path, you apply the first law of Newton. Parallel to the path, you apply the second law of the Newton. So here is the developed system. So the skier is represented by a dot. This means we have lumped all the mass property of the skier into one single point. And that point, all forces acting are the normal force, the contact force, and the gravitational force. So to solve this system, you have to pick a coordinate system parallel to the surface and normal to the surface. And normal to the surface, first law of Newton, net force is equal to zero. Parallel, second law. All right, so this is a one-dimensional elevator problem. And here we want to find out the tension inside the cable for two scenarios. The elevator goes up, so you represent the elevator with a lumped mass, and then the system is chosen, so the acting forces are gravitational force and tension. So the net forces is the resultant of these two forces together. And then, because this is an accelerated motion, you apply the second law of the Newton, and then this is how we find the tension inside the cable for the given scenario. All right, so this is the multi-choice question we had. The friction force is a function of the heaviness, but the coefficient of friction is not. So this system does not rely on the weight of the skier. Third law of the Newton, action, reaction. Any two objects in contact, you develop a pair of the forces. They don't come as single force, they come as pairs. So action, reaction, they are equal in magnitude, opposite in direction, and we designate them with AB and BA. So one is action, one is reaction. That is the third law of the Newton, fairly simple. So these are examples. So for the same reason, with that horse, the way and reaction force should be equal. They are action-reaction. And all right, so